Good morning. So this is just a quick video and the title is Space Filling Fractals to Visualize Randomness. Now when I speak of fractals, in this video we're not really talking about the kind of fractals that you might be most familiar with. Something like the Mandelbrot set or the Julia set. Now when these sets were first discovered, the people were absolutely astounded and surprised that such complexity and beauty could be generated from such simple iterative functions. I am still absolutely astounded that those sets exist, that out of the abstract, from simple iterative functions, just such immense beauty and complexity can come forth. I think it's analogous to the way that out of the physical universe, us and the physical world, again, such incredible beauty and complexity, much more so than the Mandelbrot set, has come out of such kind of simple primitives, like the workings of atoms and so on, if you can call them simple. I think these things are analogous. So those types of fractals are going to be similar to the fractals we're going to look at, in the sense that they're generated from iterative functions, have kind of self-similar properties and so on, and have fractal dimensionality. But we're going to look at much simpler fractals. Now, and what we're going to do is, fractals all have a self-similarity to them. And the interesting thing is that that self-similarity can be looked at as being, that regularity can be looked at as being a measure of randomness, which is quite interesting. That's turning things kind of upside down. And we can exploit that by then creating a fractal which is irregular, which means that the kind of input that we use to generate the fractal was regular. So we get randomness in our fractal, or irregularity in our fractal, when our input is regular, i.e. has structure, and we get structure in our fractal when our input is random. The reason I'm talking about this, I mean, I looked at this the first time probably 10 years ago, but this has been around for a long time. And initially, there was a paper by a person called H.Joel Jeffrey entitled Chaos Game Representation of Gene Structure. And what this person did was use the idea of space-filling fractals in order to visualize DNA sequences. Now, DNA sequences, the base pairs occur with non-random frequency. So they are regularly distributed, which means that when we create a fractal representation, the fractal is irregular. It doesn't collapse onto its attractor. Things you'll understand what I'm talking about when I show you later. Which means that we can then see patterns, essentially, that break that regularity that we'd expect from a self-similar fractal, and different genes will produce different patterns. So we're going to introduce this the way that it's introduced in the paper because it's a nice way to look at it. If we take 3 points on a plane and we draw a triangle with them, then we'll label these points with numbers. And these are going to be the numbers that we'd see on a dice. We start at this point, and then we then take a dice and we roll it. And then depending on the number that comes up, we take a particular action. The number that comes up is going to specify one of these points. So if a 3 comes up, it specifies this point. If a 4 comes up, it specifies this point. If a 5 or 6 comes up, it specifies this point. If a 1 or 2 comes up, it specifies this point. So we're essentially just randomly choosing one of these 3 initial points. And if we play this game, so we'll start here, and imagine we roll a 3. What we then do, and this is called an iterative function, we take the point that's between these 2 points and we draw a dot. So it's the midpoint of these 2 points. We then say that we're here. And we do the same again, we roll the dice again. And the dice gives us one of these 3 points. So perhaps it gives us this point. We then draw a dot in the midpoint, between here and here. And we're now here. So we roll the dice again, perhaps we get this point again. Oh, now we're here, roll again, maybe we get this point. Roll again, maybe we get this point. So, if we play this game, what do you imagine would happen? Now you might imagine that the triangle is just going to get coloured in completely. But interestingly, that isn't what happens. What happens is we get a fractal called the Sierpinski triangle, named after the first person who found it. It's funny, when they have kind of Russian names or Eastern European names, it always sounds more sophisticated. But so this Sierpinski triangle is a fractal and it looks like this. So that is called the attractor for this iterative function system. And an iterative function system sounds complicated, but all it means in this case is start at a particular point and keep drawing dots between whichever of the 3 original points is your next random point. And you draw halfway between your existing point and that point, and you just keep repeating that process. So the attractor for these 3 points in a triangle is the Sierpinski triangle. But this only works if the input sequence is completely random. So let me illustrate that this does not work if the input sequence is not random. And I can show this very easily. So imagine we start here and we roll a 3. So our dice is like weighted. So we always roll a 3. So the first point is here, then we roll another 3. Oh right, we're halfway between there. Now we roll another 3, we're halfway between there. Now we roll another 3, we're halfway between there. So you can see we're just going to approach this point ever more and more closely, forever. So all we're going to have is that pattern at the end of it, if we just continually roll 3s. So what you can see there then, is that if the sequence of vertices that we select is not completely random, we'll get a pattern which is not the Sierpinski triangle. So it's not the attractor of the iterative function system. If we, for example, select only 2 of the points, we're going to get something kind of in this region. So let's just have a look. So say we choose, we just get 3, 2, the pattern 3, 2, 3, 2 repeated. So first of all, let's say 3 and 5. 3 and then 5, and then 3 again, and then 5 again, and then 3 again, and then 5 again, and then 3 again, and then 5 again. So you can see that we've converged on this point, and that's the attractor of the system when we start it with those initial conditions and give it that particular sequence of inputs. So the attractor, given starting at any point with a random sequence of inputs, will be the Sierpinski triangle. The attractor for a non-random sequence will be different depending on which point we start at and what that sequence is. If it's a regular sequence, we'll only get a few points. I'll just show you a couple more examples that I've made the computer generate. So here is a example of the Sierpinski triangle where 2 of the points are visited with a random proportional frequency of 45% each, and the last point is visited with a frequency of only 10%. So 90% of the time it goes to the other points, it generates those points. And you can see it's kind of you can see the pattern, the Sierpinski triangle pattern is kind of faded towards the point that it doesn't visit. So you can see then that essentially the degree of regularity in the input sequence determines the pattern that we see, or the degree of irregularity, if you like. So that's a Sierpinski triangle. Now, you don't have to do this with just 3 points. You can do this with 4 points, with 5 points, 6 points, 7, 8 points, and you get different attractors. So with 5 points, you don't get the Sierpinski triangle, right? Because you're starting off with a pentagon. Now, what's interesting about this, and what H.Joel Jeffrey noticed, is that if you start with 4 points, so what is the attractor for this? So if we imagine we've got, we need a kind of random number generator for this, and we're just generating these numbers in randomly. So imagine we start here and we generate a 3, then we go halfway between this point and draw a dot. Now we generate a 2, we go halfway between this point and draw a dot. Now we generate a 3, we go halfway between this point and draw a dot, and so on. What does the attractor look like? Well, in this case, the attractor does fill the space. So if this is a random sequence of inputs, it completely fills the square. Now what Jeffrey did with this, so similarly to the triangle, if the sequence is not random, then we don't fill the square. Again, we can show obviously if we kept rolling a 2, then we'd just go here, 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 and obviously that's not filling the square. Clearly, when the entropy is so low, i.e. the measure of disorder is so low, then we just end up with a very simple pattern. And what's really interesting about the four-pointed chaos game, or whatever we want to call it, is that it's quite sensitive to the sequence of inputs, to the extent that what we get if we put the inputs in, non-random inputs, we get kind of patterns that we can visualize. And so Jeffrey did this with DNA sequences, because DNA sequences have 4 bases, C, G, A, and T. So he labeled them C, G, A, and T, and he then plotted the DNA sequences in this manner, just looking at the base. So say it started with a C, started at this point. The next one's a G, goes halfway between that point and that point. Next one's an A, goes halfway between that point, and so on, until he'd gone through the whole sequence. And what he got, I'll show you the pictures now. So that picture there is the human beta globin region on chromosome 2. That's what it looks like. There's some other things in here. If you can see that. So we've got some proto-oncogene and some other proto-oncogene on the left and right. And you can see that you get patterns which you can tell apart. So it's really easy to write a program to do this on any input. So I've written a program, it's probably been done before, but I just wanted to see what would happen, where you can use any binary input as a random sequence to generate a space-filling fractal, starting with 4 points. Of course, when you've got binary input, that means each byte has a value between 0 and 255. And that means we have to quantize the range. So we can say something like, if it's between 0 and 64, then we'll map it to a 0. Whereas if it's up to 128, we'll map it to a 1. Then if we go up to 192, we map it to a 2. And up to 255, which is the maximum value you can represent in a byte, we'll map it to a 3. So that from a random sequence of bytes, we can quantize each byte and it will give us a quadrant, so it will give us one of the 4 corners, so that we can then produce a random pattern. There's probably more interesting ways to do this. You know, we could use something like polar coordinates and map each of these to an actual angle and then fill in segments, something like that, you know, if we cared more about the values. But it turns out that even with just this simple quantization, you can get some quite interesting pictures. So I've done this, and now I'm just going to show you the pictures. So I've got my simple program here, and it's called Randomness. And what it does, it takes an input, it takes the length of the image in pixels, so that's just how big it is. The number of bins, that's the number of quantization bins. To get a clear image, just use, if we use 2 bins, then the image will be, the output will just be red on black, and there won't be any shading. For more complicated inputs, you might want to have shading. And then you specify what the output image is. So to give an example of this, and I'll show you quite some bizarre examples. So on my system, I use the browser Chromium. So, and its binary is located at user local user local share Chromium Chrome. So if I call ranviz with that, so this is the executable that I'd use for my Chromium browser, and we're going to see what it looks like when visualized. And we'll say we want it to be 1000 by 1000. We're going to use 2 bins, and the output, we'll just call it c.ping. It's just processing it now. Now the Chromium binary is pretty big, so it takes a little while, but now it's done. So now if we load that image, we can see that the Chromium binary looks like that, which is quite interesting, right? Of course, the length of the binary is going to make quite a lot of difference, because we're going to fill more space with a bigger file. So to be fair, we should really compare files that are kind of the same length. So that's what Chromium looks like. Let's do the same command again, but what we'll do is we'll use Inkscape instead. I don't know if you've used Inkscape. We'll see what Inkscape binary looks like. Just out of interest. Takes a lot less time to process because it's smaller. And there you go, there's Inkscape. So isn't that curious? And that's clearly different in character from Chromium. So we can tell apart these two programs by their kind of signature as a space-filling fractal. And I often thought about this and thought perhaps you could do something like you have a visual way to check the integrity of files, and just a glimpse to see if something is amiss. Maybe you could develop something based on this. So what else have we got? I've created a few of them. I'll just go through some. So that's Chromium. This is an MP3 of Claire de Lune. It's basically filling the space. That's the FreeBSD kernel. That's Inkscape. So you can see the difference between the FreeBSD kernel and Inkscape. But you see some kind of similarities as well. And that was the program itself, the ranviz program itself, visualized. And it's not very long, so there's not a lot of points. And there's a Sierpinski triangle. So you can see that you can actually then visualize pretty much any binary sequence. This can probably be improved in lots of different ways, and programs will tend to have certain repeated structure, especially if they link to static libraries. They're going to have sequences which are similar, so all that would really needs to be looked at closely to try and get good maps of programs. And what you might want to do is, instead of just looking at the binary sequence, disassemble the program into assembler instructions and quantize those or something like that to get more of a flavor of what the program looks like visualized. Because just to clear up a point, when we're talking about a random sequence, it's the sequence that's important, the actual sequence, so whether or not you have structure in the sequence, like going 2 3 2 3 2 3, that would be not random at all. But 2 2 3 3 2 2, like random sequences of that would be random. Okay. For completeness, we should cover the iterative function part. So let's do that for the example of the square. So this is our square, and we give it the points A, B, C, D. The points of that square, the coordinates of each of those points can be anywhere, but let's pretend that they're at the vertices of a unit square. So we've got 0, 0 for x and y, so it's nowhere. We're going to say that b equals 1, 0, there's 1 in the x direction. C equals 0, 1. It's 1 in the y direction, 0 in the x direction, and d equals 1, 1. I just want to write this in a way that's easier to understand, so easy to use in our iterative function declaration. So we could say that a dot x equals 0, a dot y equals 0, b dot x equals 1, b dot y equals 0, c dot x equals 0, c dot y equals 1, d dot x equals 1, d dot y equals 1. And now we also need something to represent our current point, our point that moves around and plots things on the square. So we'll just call that p, just for the sake of it. So we've got p dot x equals a dot x to begin with, p dot y equals a dot y. Now we're going to introduce a time script so that we can say what we're talking about. We'll say that p at time t, or rather p dot x at time t plus 1, so the next time step equals half times p dot x at time step t plus a half of whatever we're going to. So say we go to d, so half times d dot x. Does that make sense? And then we'll say that p dot y at time t plus 1 equals a half times p dot y, so half of the original value, plus a half times d dot y. So that's how you do it algebraically. You can write that a bit more succinctly because of the way that vectors are added up. We can actually, if we just assume that these are vectors, so that a equals 0, 0, and so on, then we can say that p at time t plus 1 equals a half p at time t plus a half of whatever our vertex is, so a or b or c or d, whichever one we're moving to. And then we keep doing that. So the function iterates because at the next time step it's always based on the previous time step. That's an iterative function, and that's where this idea comes from. Well, there you go. I hope that was interesting to watch or useful, and thanks for watching.